Fitting linear models to data. Real-world data seldom lies exactly in a straight line with a consistent rate of change. But there is a lot of data that is close to being a linear model. This particular data set is tuition at LBCC from fall 2000 to fall 2009. I've gone ahead and graphed the data. As you can see, in general, tuition goes up as time goes by. We can draw a line through the data. We won't be hitting every single point as we draw this line through the data. And everyone who draws a line will draw a slightly different line, but we can see there's what we call a linear trend to the data. In general, tuition's going up at a fairly consistent rate. We can find an equation of the line through that data by picking a couple of points. So I think the points I'll pick here, they'll be off the line, not the original data points. So it looks like my line is going through the point 0, 35, where 0 represents 0 years from the year 2000, so the year 2000, and 35 is $35 of credit in that year. And then picking a second point, 5 years later, it looks like the tuition was approximately $55 per credit. Now, if you go through, find the slope, find the equation of the line. This gives me a rate of change of 4, and this would be $4 per year. So in general, the tuition went up $4 per year per credit. And then our equation, the cost of a credit, started at $35 a credit for the base year, plus an additional $4 per credit for every year after that. Now, you may have drawn a slightly different line through that data. The next time I drew the line, I might have drawn it slightly differently, but we'd probably all come up with equations that are fairly similar to each other. And so this is called a trend line, mimicking the trend through the middle of the data. Once we have an equation, we can use it to make predictions, either predict the tuition for a given year or predict the year when the tuition was a certain amount. Now remember, t, our independent variable, represents the number of years since the year 2000. So if I let t be 15, this would represent the year 2015. And we can see what our model predicts for the tuition in that year. So our model was 35 plus 4 times t. Now I'll replace the t with the 15. And our model is predicting tuition being $95 per credit in 2015. And as you might know, that is a little bit low. If we use our model to predict in what year the tuition first hit approximately $50 a credit, we'd be putting the 50 in for C, and then solving for T. And looks like I'm getting a fraction for an answer. So the model's predicting that late in the year 2003, not quite in the year 2004, was when the tuition first hit $50 credit. We go back to our graph. That seems reasonable. In the year 2003, 2004, our tuition's first getting up around $50 per credit. When we make predictions, they fall into 2 different groups, what we call interpolation and extrapolation. Interpolation is when we predict the value inside the domain and range of the given data. So our solution that in 2003, 2004, tuition was approximately $50 per credit, those input and output values are within the domain and range of the given data we started with. That's an interpolation, and we got a fairly accurate estimate for that. Extrapolation is when we make a prediction outside the domain range of our data. So when we tried to make a prediction for the year 2015 and came up with tuition being a mere $95 per credit, as you know, tuition's already quite a bit higher than that, we didn't get a good prediction. So data like this, it's modeling approximately what's happening, but you have to be careful when you're extrapolating beyond the data, making predictions outside the domain and range of our data, because the situation may change, and the trend that we observe for original data may not hold in the future. When we came up with the model by hand, again, each of us would have slightly different results, depending on how we drew our line and what 2 points we picked off our line. But it is pretty simple with modern technology to put our data into a calculator or a computer and let the calculations be done for us, in which case we'd all come up with the same model for a set of data, and the model will be something we call a best fit line. So I did this particular graph in Excel, and the equation here is similar to the equation I got by hand, but it would be a better line than the one I got by hand. The directions for coming up with this least square regression line using a TI graphing calculator or using Excel are given on a separate video, so you can watch those to see where I came up with this equation. Okay, so what did I mean by a model with the best fit? Why was that one that I got off of Excel better than the one I got by hand? What it does is very quickly goes through and finds a line that minimizes what we call the squared residuals. It minimizes, if I draw a line in here, again, the line doesn't hit every point. Some of these points are underneath the line, some of these points are above the line. This point is a little bit below the line. This one's a little bit below the line. These next two are quite close, next three. This one's above the line. This one's below the line. So each of these red lines I'm drawing in here is how much my trend line is off from the original data. Those are what we call residuals. We want those to be as small as possible, and so with the best fit line, the calculations are done to make those as small as possible. And what those distances are give us an idea of how good our line fits the data. The smaller the total amounts of those red lines are, the better the line fits the data. The measure of how well it fits is something called the correlation coefficient. And again, this isn't something you'll have to calculate by hand. Any computer program that finds a least squared regression line would also calculate the correlation coefficient for you. So you don't need to worry so much about how to find it as what it means. The correlation coefficient will be a number between 1 and -1. If the correlation coefficient is positive, that indicates we have a positive trend, a positive slope to our data. So here, r equals 1. And if we draw a trend line in there, it would hit exactly every single point. In this particular data set, these points do line exactly in a straight line, and we've got a perfect correlation of value of r equals 1. 100% of the data is touched by the trend line. This second data set has an R value of 0.369. If I try to draw a trend line through here, it's pretty hard. Does that look good? Does that look good? There's not a good trend here, and that's reflected with this R value of 0.369. It's very close to 0. If an R value is close to 0, the trend line that you might draw in there is not going to be a good predictor of what's going on in the actual data set. My third one here has an R value of -0.979. So the R value being negative indicates that the trend line has a negative correlation, but it is very close to -1. If the R value was exactly -1, then all these points would line up exactly in a straight line. This one's got a little variation. We've got a little bit of a residual there, but not a lot. And that's again reflected in the R value being very close to -1. So it's a very strong fit.